Hello, my name is Kiyana Maynard, and my presentation today is on enhancing behavioral performance via the use of repetitive transcranial magnetic stimulation. I did this study with the T&E lab. Okay, introduction. What is TMS? Basically, TMS is a non-invasive procedure that produces stimulation of the brain tissue via a magnetic field. The pulses will emit a small electric current that will change the firing patterns of neurons. Specifically, in this study, the use of RTMS or repetitive transcranial magnetic stimulation is used, which basically just means that the pulses are being performed with a specific repeating pattern. We're doing this to induce plastic changes in brain circuits. But you know what? Like, why even use TMS? Like, what can it help with? TMS is used to treat various psychiatric disorders, including depression. Simply put, TMS stimulates and resets specific areas of the brain that regulate your mood and provide relief and basically break the cycle of depression. However, for a significant amount of people, it doesn't really work. So the basis of the study is just to make it more effective. Some background that we kind of need to understand. A brain state, what is it? In the broadest sense, brain states are often referred to as states of, for example, wakefulness, sleep, anesthesia. For this study in particular, we've defined it as brain activity that fluctuates as it adapts to internal and external demands imposed throughout daily life. How does this how does this apply though? The fluctuation. Fluctuation in brain activity can actually affect how stimulation interacts with the brain. So being able to leverage those fluctuations in brain states may be a way to make TMS therapy more effective. Cool. Cognitive control, what is this? Basically, it's the ability to direct your thoughts and actions to meet your goals. For example, choosing to study for an exam and avoiding the urge to like check Instagram. Um, Cognitive control, side note, is impaired across basically every psychiatric disorder. So that disruption in cognitive control can be why people get stuck in maladaptive thought or behavior patterns, i.e., feeling unworthy, assuming the worst will happen, etc. That was sort of a side note, but it's not a side note. Um, how does this pertain to the study? Well, cognitive control is the dorsolateral prefrontal cortex dependent, and it is used for the target for a lot of stimulation therapies. So if we manipulate activity in DLPFC by cognitive control, then we may be able to leverage those brain states I talked about earlier. What's the hypothesis? Well, the hypothesis is repetitive transcranial magnetic stimulation that is applied during an active state of cognitive control will enhance the brain function at a more intense level than if the brain is not engaged in a cognitive control circuitry. Interesting. How do we do that though? Well, here's the experimental design. Basically, we have healthy participants, so participants that don't have diagnosed psychiatric disorders, and they complete two sessions. The first session they get RTMS with the combination of a cognitive control task. The second one, RTMS applied without cognitive control being engaged, so with our perceptual task. They basically come in, they get the single pulse TMS. We determine the threshold, um, so the resting motor threshold at which, I'm sorry. We do this to kind of determine the intensity at which the RTMS application can be set at. And then we also are determining the area at which we're gonna place the TMS machine on the scope. Once that's complete, they continue on doing the top X without TMS. Once they finish that, they do top X with TMS, and this is where we're engaging cognitive control. We're engaging cognitive control, and we're applying our TMS. Once they finish this, we do top X, no TMS. The pre and post TMS are pretty important. This is where they are important. This is where we're going to look at the difference in the data. So, is there improvement? Is there a decrease in improvement? All of that stuff. Once they finish that, they do single pulse TMS again. That's the first session. This second session is basically the same. The only difference is we're not engaging cognitive control. What is top X? What was I talking about? Well, it's the translational orientation pattern expectancy task. Basically, we're sitting participants down in front of a screen, like I am right now. The monitor is then going to produce different patches, different sequences. And you can kind of see these different sequences in figure 2B. The A and X, those are our target sequences. This is what we're showing the participants more often than not. And when the screen does pop up with the target sequence, they have to say, yep, it's valid Q, it's a valid probe. They use the keyboard to do that. And they're doing this as fast as they can. Um, and we're doing this to create a habitual bias response within the participants. But, like, why? Well, if we want to engage cognitive control, we kind of have to get them to go, like, get used to one certain thing, go like, this is it, this is it. So then when we do throw a distractor in there, they have to engage the cognitive control and go like this is not the valid cue, or this is not the valid probe. This isn't valid. And that's how we're gonna engage cognitive control. And we're doing this with the RTMS being applied. And then for the perceptual task, when we do not engage cognitive control, it's pretty similar. They're gonna have that computerized game in front of their face, but they're basically just kind of determining the orientation of them. The basis of it is cognitive control is not engaged for that one. What were we looking at though? What were we kind of like observing? Well, we were looking at accuracy and reaction time. For accuracy, we saw that the interaction of task pre to post with RTMS, cognitive control, and perceptual was significant with a p-value of 0.009. We saw that RTMS enhanced the accuracy performance on a cognitive control task only when it applied during that task. When applied during the performance of the perceptual task, RTMS did not enhance the accuracy. So we can see this in the figures to the right. That's the raw accuracy data. It's nicer to look at the one further to the right, in my opinion. It's a bit more simplified. It's the ratio of accuracy. So we're gonna see that top X is at an increased level compared to perceptual. It's has a improved accuracy rate. And then we performed a t-test and the p-value was 0.036, also statistically significant. For reaction time, we have a p-value of 0.074, which is not statistically significant. Yeah, it's not statistically significant. I don't know why I put significant right there. Ignore that. Um, we saw that the difference in reaction time from pre to post is slower in perceptual and faster in cognitive control conditions, but is not like enough to kind of say, yep, this is a significant result. Um, you can kind of see it in figure B. It's a little bit better. You can see that improved reaction time in the top X compared to the perceptual, but when we did the t-test, we saw that the p-value was 0.094, so not statistically significant again. So, what's the big takeaway? Basically, our hypothesis was supported. It did enhance behavioral metrics. It didn't enhance reaction time was not statistically significant, so I guess it was partially supported. We saw that the effects observed after the completion of RTMS created plastic-like changes in brain function, outlasting the time of stimulation. Woo, wonderful. Um, and then we also saw that engaged target brain circuits during stimulation can produce more favorable effects of RTMS. Where can we kind of go from here? Well, this project kind of highlights the importance of the state of systems being simulated, so the brain state. It shows that the system's initial state has been basically overlooked, and that this study helps provide understanding our mechanisms in which RTMS can restore brain function in mental illness. This basically will just overall aid in the continual application of RTMS in clinical settings, making methods more effective, reliable, and accessible, which we love, obviously. But basically, that was my study. Um, these are my references. And then a special thanks to Erin McGines and then our PI, Alec Widge.